So we're going to continue our discussion in the concrete context of how we try to understand linear transformation. But here, as you know, you might have studied matrices, but you can see the application or the how the linear transformation or this finite dimensional vector spaces, how we can see them in our understanding of matrix transformations. The way we have linear transformations, we will go for first recap some of the understanding some of the things which you might be aware of matrices. So in that context, we can say that it's an important linear transform. It's an important tools. So linear transformations. It's an important tool in the study of linear transformations. On finite dimension vector spaces. In the concept of and in finite dimensional the important study tool in the study of linear transformation on finite dimensional vector spaces. This is in the concept of matrix. So linear transformation is a so this is the you emphasize it that it is important. So although its application is more robustly can be seen in finite dimensional vector spaces, but still we can just begin with like this. But if you define, for example, define the definition of linear. So for example, let V be an n-dimensional vector space. Vector space, and let chi or be the elements which contain x elements, be any basis of V, and let A be linear transformation on V. So since every linear transformation we have, so we can have any linear transformation can be defined like this, where this J goes from 1 to so on and so on. So we can define this any linear transformation like this. So what is alpha I, j? These are the indices. I and j are indices. The value of I and j can go from 1, 0, whatever to n. And similarly j can go from. So you can have this understanding can also be had as if you are trying to understand matrix multiplication, in which rows and columns, for example, are multiplied. And in a typical matrix multiplication, if you multiply two matrices m cross n, n cross m, n cross l, the matrix which is it will be m cross l. So how you can see the application of, for example, a matrix. For example, a matrix alpha ig is usually written as in the form of square array. It can be written as a11, sorry, not a11, alpha 1. So you can have this alpha 1 1, alpha 1 2, and alpha 1, alpha 2 1, alpha 2 2, alpha 2, and so on. So alpha n1, alpha n minus 1. Sorry, alpha, this is alpha n minus 1, alpha n. So it's a general way we define. So alpha 1i, alpha i2, so they form a row, and alpha ij, alpha 2j, and alpha nj, this is alpha in, they form a row and they form column. So this doesn't define matrix, this defines matrix. So this is not a matrix, this is matrix defined under certain conditions of linear transformations. Which are defined like this. So if you remember, there's a vector, there's a scale, so this is the linear transformation, and this matrix can be defined vis-a-vis this transformation. There's an interesting sentence. So it's the so you can normally write why you should write this transformation as axj alpha ij xi, and not as xia is equal to sigma j alpha ij x. Then here it will be. So what should you write it? So normally we write it like this: axj is alpha ij xi, axi is. So why should you write this instead of this? Instead of this, we are normally writing this. So that's you can think of. Now what we can do is we can have a linear combination. So now what we can do is having I don't have a duster. Just wait 1 second. So you can. So you can have linear transformation. So what we can do to state our rule, so any linear combination, and we write this. So if we define, for example, so if we consider and I and j are the row and J are the column matrices. J is the column, I is the row matrix. So now what we are going to do, if we consider the differentiation D on the space Pn at the basis on the spaces sorry, Pn with the basis x1 so on and so forth. So what will we get? So if you have a particular operation of the way in the linear transformation, we are going particularly showed when we had an operator, a differential operator, and we try to define linear transformation, that way commutativity as a property got violated. In the same way, we have to use this linear transformation. We will use operation of differentiation in this matrix form, which satisfies, which we have defined as a sort of in terms of linear transformation. We see how will it will pan out. For example, what is the matrix of B in this basis? Which basis? Basis in which we have defined xi t is equal to ti minus 1, where I goes from 1 to n. So we have defined a function x in terms of t raised to power I iota minus 1 or I minus 1. So now if we define it this way, and we have a differential of an operator on the left hand side, so d of x1 will be, so 1 minus 1 will be 0, so it will be the first thing will be 0 times, so it's tx, the multiple of that thing, t of x, when we define a linear transformation. So t can be defined I minus 1. So I is 1, so the first will be 0, and so on and so forth, the first row. The second one will be 2 minus 1 is 1, so on. And so first let me write it algebraically. Let me write it first algebraically, then we can write it. So it will be dx1 is 0x1 plus 0x2 so on and so 0xn minus 1 and 0xn. The same way dx2 is equal to 1x1 0x2 0xn minus 1 plus 0xn. In the same way dx3 0x1 2x2 0xn minus 1 plus 0xn. So if you just, first will be 0, second will be 2 minus 1 1, third will be 3 minus 1, that's 2, then it will be 4 3 4 and so on and so forth. So if you want to write it, you can write it as d of xn will be 0 of x1 0 of x2 n minus 1, this is last, plus 0 of xn. So if you want to write a d in terms of this as a differentiation, so you can write it like this. So 0 1 0 0, sorry, 0 0 0 0, then it's 2 0 0 0, then it's 3, and so on, and it will be 0 0 0 so on, and n minus 1, and the last may be 0 0 0 so on and 0. So if you so you can, so this is an unpleasant phenomenon of indices. when you compare them vis-a-vis 1 and 2. Now, the other thing is that how we can define matrices and transformations. Matrices and transformations. So matrices and transformations. So what's the problem? To define the problem is like this. In a fixed coordinate system, coordinate system where this is how we define in terms of these things. Knowing the matrices A and B, knowing the matrices of A and B, how can we find matrices of the form alpha A plus beta B of AB of 0, 1, etc. So in a fixed coordinate system, where this is known as this, knowing the matrices A and B, alpha A may be scalar, beta B is scalar, this is the way of AB, of how can we define, how can we find matrices of 0, 1, etc. of the form which will have this thing. So that now A can be defined as the way we define it in terms of indices, alpha ij. So we can, these are different rules, and so alpha can go 1, 2, 3, j can go from 1 to n. In the similar sense, B can be defined as beta ij. Now you can have C in terms of alpha A and beta B, alpha A plus beta B. So so you can also define C in terms of gamma ij. So how can we define gamma ij in terms of this alpha ij and beta ij? So that's the point. So gamma ij is alpha ij plus beta ij. And also, so this is the point. So if you want to define it in terms of elements 0 and 1, the linear combination of alpha ij and beta ij in terms of 0 and 1. So you can have 0 is equivalent to, so 0 ij, that's understood. 1 is equivalent to eij. Or ij is equivalent to 0, or eij is equivalent to, this is Kroneker's delta. So in the same manner, you can say that a more complicated rule is defined as, C is defined as AB and C is defined as gamma ij. So maybe this alpha ij can be written as alpha ij or rather I would say gamma ij. If you want to write it in terms of alpha ij and beta ig, we can write it as sigma k. So you can have some of the indices, they get absorbed or they get thing once we have the way we have the normally when we define matrix multiplication, if you have rows and columns, and then if you have to, if you had these rows and these columns, sometimes these columns, so it will be have the matrix multiplication is defined. So you have one of the indices got somehow absorbed, or it got it did not work out. So in the same way, how can write this gamma g ij in terms of alpha ij and beta ig, such that repeated indices will not turn out in the larger thing. But the thing is that what you have to define what is the repeated thing, and so such that we can write alpha ik and beta kg. So this is repeated index. So this is the rule of n here. The way we have n and got this thing. So it got cancelled somehow in the multiplication process. In the same way, we can define gamma ij in terms of alpha ik and beta kg. If we define k as sort of repeated indices, or the way we define matrix multiplication. So gamma ij can be defined this way. So through this we have to use the definition. So the longer way of saying the same thing is that we have to define a definition of matrix associated with a transformation and juggle. Such that or further it can be written as so A times so we can write it like this. So in the end we can write it as B times sigma I so you can write it like this, C, so you can see BKJ alpha I KJ. So we can write it as alpha IK BK XI. So it's a rearrangement of these indices. So you can rearrange them things this way, or rearrange them putting this he as a scalar multiple of this and keeping it. So this is how we restate a property of this multiplication. The scalar can also be written like this in that sense. So the point is now the another point which will just conclude this thing. There is a certain theorem. The theorem says that the theorem says that among all a set of matrices alpha ij, beta ij, etc., ij goes to 1 to n, not considered in the linear transformation, we define some scalar multiplication product and y. Y, we can define it as alpha ij plus beta ij. We can define it as alpha ij plus beta ij. So among all set of matrices, alpha row and column, where I and j goes to this, we define some scale. So it's simply how we can. So we can check it also. So if alpha ij is in a matrix and beta ij is another, so can we write it this way? Can the matrix addition be possible as a property? So in the same way, we multiply this alpha ij as a scalar. So it's outside the brackets. So you can see can alpha ij. This is another property. Now the property of another alpha ij and beta ij. So again, can we write it in terms of some repeated index or not? So we can have the way we defined previously as a k, one of the repeated index. So we can write it as, we can have it alpha I k. So we have kept I and j, but we define some repeated index k as kj. And again, the property of 0 ij is, so you can either be ij is equal to 0 or by canonical delta function, it's 1 or 0. Now, there is a sort of isomorphism or one-to-one correspondence, which shall preserve all of these linear transformations, and that can be defined. So, if so we can that can be defined as an arbitrary coordinate system. If we that can be established if there is an arbitrary coordinate system with coordinates x1, x2, xn of an n-dimensional space, of an n-dimensional vector space, D between all linear transformation. A on V and all matrices described by so it's an isomorphism. So in other words, there is a one-to-one correspondence, or rather this way, there is a one-to-one correspondence that should preserves the sum, the multiplication, and product. Product is this one of and scalar multiplication also. Scalar multiplication also. Rather, I would say sum, scalar multiplication, and product also. So this theorem, the aim of this theorem is to show that these properties are somehow preserved in an isomorphic manner. There's a once before transformation and after transformation. There is a one-to-one map or one-to-one corresponds to each element from one side to the other side. So we'll stop here, please.